Okay, here we go. Hello, everyone, and welcome to our 48th web seminar of the series of Latin American webinars in physics. My name is Joel Jones from the PUCP in Peru, and I'll be your host today. Our speaker is Werner Porod, who is a professor at the University of Würzburg. He will talk about the interplay between SUSY, neutrino physics, and the LHC. So Werner received his PhD from the University of Vienna and has carried out postdocs at DESY, Valencia, Vienna, and Zurich. And he's probably best known for being the author of SFIMO, among other pieces of useful code. So Werner's talk today is titled Supersymmetry, Neutrinos, and the LHC, and we're very happy to have him as our speaker today. But before we start, we'd like to remind you that after the talk, you can be part of the discussion by writing questions and comments via the YouTube live chat system. I'd also like to remind you, hopefully you can see this, to check our WordPress, Facebook, and Google Plus pages. If you want to write one now, you should write the first one, because we have links to all of the other pages down there. So remember, it's lawphysics.wordpress.com. Okay, so after this, I'll hand you over to Werner. So let me, okay, so they're all yours, Werner.
Thank you very much for the introduction. It's a pleasure to speak here. Before I start, I want to say that's the first time I'm doing this type of presentation, and I know the question should be at the end. However, I know also that if nobody interrupts me, I have a tendency to be very fast. So please, if I get too fast, please interrupt me nevertheless of your rule. So I'm now going to switch to the slides. As Joel has said, I'm going to speak about supersymmetry, neutrinos, and the LHC. I will have mainly two topics. The first one is the implication of Higgs discovery and the beyond the standard model searches at the LHC for model building. And then I will focus on a special class of supersymmetric models called Natural SUSY. I will briefly discuss the MSSM context, tell you why I'm not that happy about this class of models, and how the problem that I see there can be solved in an extension thereof. Well, let me start with a well-known result, namely Higgs physics, which was the last part of the standard model which needed to be discovered. Its mass has been measured with a very high precision to 125 plus 1 plus minus 0.2 GeV. This year there was an update within the uncertainties that's consistent with the previous measurement from 1.1. What's also important, beside the mass measurement shown here, is the measurement of the relative signal strengths. So the mu parameter that you see here on the axis, that's the ratio of the measurements over the standard model prediction. So for example, the mu gamma gamma is the production of a Higgs boson, which then decays further into gamma gamma, divided by the standard model prediction. In a perfect world, if the standard model were correct, let's assume that for a moment, this would be the correct description, then everything should be on this dotted line here. And as you can see here, the error bars, uncertainties here are within 1 sigma. There's more or less consistency between standard model predictions and the measurements. This hasn't changed too much with run 2. It's even getting somewhat closer to the standard model prediction than you see here in the picture. But essentially the same remains here. Now, if now looks at the value of the Higgs mass, it has been measured to 125 GeV. Now, in supersymmetric models, in contrast to the standard model, the Higgs mass is a prediction. Particularly in the MSSM, it's essentially bounded at tree level by the Z mass, and then I need radiative corrections to get it to larger values. This can be accommodated thanks to the large Doppler coupling, but what one has to look at is actually not the mass, but the mass squared. And if you look at what 125 GeV squared means, then that's the Z mass squared plus approximately 86 GeV squared, which means we have order 80 to 90% corrections. Remember, the Z mass and upper bound is not actually the value that you get in the MSSM, which means you have huge corrections. We can do that because the Doppler cover coupling is order 1, and therefore we have large corrections. However, as we will see, this drives us in a part of parameter space which is somewhat uncomfortable. At the same time, LHC has not only looked for Higgs, but also for physics beyond the standard model. And it can be unfortunately summarized on this slide. A lot of exclusions, but no signal. So what does this mean for model building, in particular for supersymmetry? Well, before coming to that, let's ask first the questions. Do the bounds imply that supersymmetry has to be really heavy? So the show here are two examples, one from Atlas, one from CMS. The first one is quark production, where the quark decays into a quark and a neutrino, and neutrino decays further into W and a neutrino. That's one out of many searches, but the order of magnitude for quarks is about the same. And you see here for very light neutralinos, what you see here is the plane, neutralino plane versus quark mass plane, and the neutrino is assumed to be the average of the quark mass and the neutralino mass. These kinematic assumptions define exclusions up to order 1.2 TeV if the neutralino is rather light, let's say up to order 200 GeV. But there's as a strip here where the neutralino mass comes close to this quark mass, we can go down to, let's say, order 450, 500 GeV, and this still would be consistent with our experimental observations. So the exclusions do not necessarily imply that all quarks have to be very heavy. However, they would imply that you would have a very compressed spectrum. And that's actually rather difficult to obtain in simple SUSY models like GMSB, MSUGA, and so on. So there you would need, if this turned out to be true, a very specific form of supersymmetry breaking. Similar results hold if you go for a neutrino production. They can even find bounds of up to 1.8, 1.9 TeV, depending on the exact search channel. But as there you see, close to the kinematic limit, where you have rather soft jets, because that's the reason why you can get here those low masses. Simply the cuts of the jet energy goes beyond what goes below what the experiments want to have. You still could get rather light greens, let's say order 700, 800 G. That's not excluded by experiment, but generically you find rather strong bounds. Now, what does this combination imply for the model building part? As I said before, we have a Higgs mass of 125.2 GeV. We have rather large loop conclusions therefore, and this implies that the scalar partners of the top quark, the so-called stops, have to be rather heavy, and or we need in addition large left-right mixing between the stops. Just to remind you who are not so familiar with supersymmetric models, for every helicity part of the top quark, you do have a supersymmetric partner, and they mix among each other. And that's caused by a so-called trilinear coupling, which is denoted by A top, or if you go up to the high scale, by A0. Now, if you look in different high scale SUSY scenarios, what you see, for example, in so-called gauge mediation, where the SUSY breaking is transferred from the hidden sector to the visible sector via gauge interactions, that there in the minimal model, you hardly have any left-right mixing. Therefore, you need rather heavy stops. And what those people found already in 2012, Ajab and collaborators, is that the stop should be heavier than about 6 TeV. The reason we have small left-right mixing, the main contribution goes roughly speaking like log m stop squared over m top squared. Of course, that's the minimal model. You can go to a more complicated model that's based on this paper by Mayday, Seiberg, and Shi on general gauge-mediated SUSY breaking. They can get additional terms. If you do that, then these people here, Knapp and Redigolo, they did a recent study last year where they really went over different variants of this type of models, and they found, well, you do get, because you get additional left-right mixing, down to stop masses equal about the spot masses if the so-called messenger scale, so that's the scale where the SUSY breaking is transferred. The minimum model is order of 100 TeV. This class of models to get so small stop and spot masses, you have to go up to 10 to the 15 GeV, so close to the gut scale. I should add here that the stop and the spot in this class of models are the lightest strong interacting supersymmetric particles. So 6 TeV, this would be beyond the reach of the 14 TeV LHC. They would really need a 100 TeV collider, as already discussed here. Now, if you go to unified models like the CMSSM or the UHM, which means that you have non-universal Higgs masses. So what is assumed here is you have universal scalar masses characterized by this parameter M0. The CMSSM, this would be the same for the scalar balance of the fermions and the Higgs bosons. In the non-universal Higgs mass models, this mass parameter would only be for the fermions, but would be different scalar mass parameter for the Higgs sector. Independent of the class of models, you find approximately that the value of this trilinear coupling, which governs the left-right mixing for the stops, has to be about twice M0. This has been worked out by several people, the details and implications. Recently, the Fidino group did take into account all constraints from low and high energy physics, which means astrophysics, low energy observables, LHC data. And they find, okay, within the CMSSM, you can do that. You have about this relation here. You would find that quarks and neutrinos should be above 2 TeV. So you might see a glimpse until the end of next year. Lepton mass about 600 GeV. This will be the lepton right. The left lepton is actually heavier, about 700 GeV. And the lightest neutralino would be order 450 GeV. You can even go to more generic high-scale models, but independent of the exact realization, usually you find we need a large trilinear parameter, which is order that's preferred from the sign. It's a negative sign between 1 and 3 times the maximum of the genome mass parameter M1/2, or one of the squawk mass parameters in the scalar top sector and stop sector at the gut scale, and then have the RGE evolution down to the low scale. The negative sign is preferred because you get an additional contribution which comes negatively with the M1/2 parameter. A nice summary has already been worked out of this class of models in 2012 by Werner, and Kulkarni. So what you see here, if you have a light stop, which means order 1 to 2 TeV, which is accessible still at the LHC, you need a large trilinear coupling. But that's actually somewhat problematic. The reason being, we have many scalars in SUSY models. It's not as easy as in a standard model. We just have the usual Higgs potential. We have a much more complicated potential. Now, when one does SUSY studies, one usually chooses a parameter set such that one calculates the mu and the corresponding soft SUSY breaking parameter p to obtain the correct electroweak symmetry breaking, to obtain the correct set mass, and so on. This approach engineers clearly a minimum of the potential that's consistent with all the data, no question about that. But it does not exclude that there are additional other minima which are potentially lower lying, which break charge and or color. So what we did in our study was to really look over the parameter space, calculate all possible extrema of the potential at the tree level, which I can do with some mathematics, and then include at the loop level the one loop effective potential starting from the tree level extrema and going then to the one loop corrected extrema, looking there which are really the minima. What you see here in these plots are different parameter combinations. The first plot, the A0 M0 plane, fixing M1/2 to 1 TeV, tan beta 10, mu larger than 10. The second one, we fixed M1/2, the genome mass parameter, and the scalar mass parameter M0 to 1 TeV, and show this in the tan beta A0 plane. The lines that you see here, these are lines of constant Higgs masses. The color coding is such that in the green area, we do have, that is the designed minimum to be the global minimum. In the blue and red area, actually it turns out that either color or charge breaking minima is lower lying than the one that you would like to have. Blue means it's, well, more or less metastable. The metastable means we took here about a 10% probability that it survived until today. And red means you're below the 10%. Of course, 10% is a very chosen number. You can switch that. You see also here by the dots, there's a lot of numerics involved, so there's some fluctuation. So what you should take is, roughly speaking, this bounce here seriously, and whether it's really metastable or unstable about the 10%, it's not that important. The important thing is here that if you look at the range, so we have 125 GeV for the Higgs mass, we can be in the stable region, but it's a large part, and in this part it's even more pronounced, where we're actually in an unstable region of parameters. And we should add here what we took here were at most 3 WEFs for the fermions, because the mathematics to get all the 3-level minima is quite involved. We find a huge number, which scales roughly speaking like the number of the WEFs that you allow to the power 3. So if you have, in addition to the 2 Higgs WEFs, 3 WEFs, you have an upper limit on the minima of 5 times to the power 3. And that's quite a bit. So the should take from here is, if you have large, in particular from this plot here, if you had large parameters in the best fit point, there is really danger that you have color or charge breaking minima. This should be taken into account for the constraints. Now, of course, these are within the MSSM and Sugra. You have to do this in more general context, but it turns out from the generic high-scale models that I presented before, this stays true, but for GMSB, they don't have the left-right mixing parameter for any minimal version. Now, if you can go to the general MSSM, as a damn part of the parameter space, color, charge breaking minima issue, but of course, you have much more freedom in the parameters. So general MSSM means you define every parameter at electroweak scale, you take into account flavor constraints, which more or less kills large flavor mixing parameters. So what's usually assumed is that everything is like in the standard model. So the only sources that you have is induced by the CKM, the PMS matrix for flavor mixing, and the soft-SUSY breaking parameters do not induce additional flavor mixing. Of course, the generic signatures in such scenarios, they are well known. Multi-lepton, multi-jet missing energy. So that's similar to the M-Sugra searches. However, what really matters here is the kinematics. So in M-Sugra, you usually have a large hierarchy, quarks much heavier than leptons, and those significantly heavier than neutrinos, neutralinos, giving rise to hard jets, hard leptons, and quite a lot of missing transverse energy. In the generic MSSM, you do have the possibility to get a compressed spectra, and as I've seen in the exclusion plots, this would mean that you can get to small mass, or relatively small masses for quarks and neutrinos order of unit GeV, consistent with all the data. Now, a subclass of this generic MSSM is what people tubed natural supersymmetry. You see here the reference which introduced those. And the basic idea is, let's keep only those supersymmetric particles light that you need to get a natural Higgs boson, which means you do not have a huge cancellation between different sectors contributing to the Higgs mass. Essentially, this means in practice that this bottom, which is the SUSY part of the bottom quark, the gluino, and the lightest neutralinos should be considered. The lightest neutralinos and neutrinos should be xenolite. Because in this class of models, the so-called mu parameter should be order of MZ, let's say up to order of UNGV. Now, if you put all the Gaussian mass parameters to, let's say, 1, 2, 3 TeV, this implies that the Higgs xenos are relatively degenerate. Depending on the ratio of Higgs mass parameter over Gaussian mass parameter, the electroweak scale, you find a mass splitting between the neutrinos and the neutralinos between a few hundred MeV up to 5 to 10 GeV. Of course, if it goes below a few hundred MeV, what you produce are usually soft ions in the cascade decays, which you do not see. This implies that actually all three of those particles, the neutrino 1, neutrino 2, and the delta strachino, are essentially invisible at the LHC. If you would go even further down, let's say to very close to 100 MeV for the mass difference between strachino and the neutrino, what you find is that you have a long strachino, and then you get, in addition to the direct searches, constraints from searches for metastable charged particles. And there you get actually a bound of the order of a few hundred GeV already. However, if the mass difference is such that there's more or less a front decay, then the bound is currently order of 100 GeV for those neutrons and strachinos, consistent with this consideration concerning the naturalness of the Higgs bosons. Now, in this class of models, essentially what you have are final states containing top quarks, bottom quarks, and W's, because what you have in the strongly interacting sector are the gluino, the lights top, the lights bottom, which then decay further into top quark, bottom quark, neutrino strachino, W's bottom or top, or the gluino decaying the top, bottom, bottom. Now, the small mass difference, as I said before, implies that in the Higgsino sector, essentially the strachino and the neutrinos are all invisible. So if you see something like a top or bottom plus missing energy, in this class of scenarios, you do not know whether they have produced a stop or bottom. Particular as the transition ratios will depend really on the nature of the stop and bottoms. And there you have hardly a handle on. One more word concerning the Higgsino mass parameters. This natural supersymmetry implies that actually the mu parameters, superpotential parameters, should be order mz up to a few hundred GeV. However, you can construct models that have a soft-SUSY breaking parameter for the Higsinos. This is possible because they come in a vector-like representation of SU2. So the Higgsino mass is actually the mu parameter plus this soft-SUSY breaking parameters. So the generic statement that I find in the literature that natural SUSY implies relatively light Higsinos might not be true if you have in addition this mu prime, the soft-SUSY breaking parameter for the Higsinos. This is just as a word of caution. Now, what's the problem with this type of scenario? If we have Higsinos as the lightest supersymmetric particles, then they have a very large annihilation cross section, which means that if you look at the dark matter aspect, those guys with this mass range of 100 to a few hundred GeV cannot be the dark matter of the universe. So in this class of scenario, you would need some additional source for the dark matter. And that's a feature which I do not like, and therefore I'm not sure whether this type of scenarios would really be called natural supersymmetric scenarios. So what are the current situation if you look now, for example, at stop searches? And these bottom searches are rather similar. Again, what you see here is an example of Atlas and CMS searches, and you see the different search channels that they have. They go up to 1 TeV for the stop mass if the neutrino mass is relatively light. What you look at, to be more precise, is actually stop decaying into top quark, be it on shell or off shell in the lightest neutrino. This holds for both Atlas and CMS. There's some area here which is not really covered because there the stop mass is approximately the top mass, and there you have a huge background from the top pair production. So there's a small gap in these plots here, but still a light stop would be possible, but it's getting smaller and smaller as the experimental techniques are refined. Now let's assume really we would have such a light stop, let's say order m top squared. We would have gluino masses of order, let's say 2, 3 TeV. And the Higgs mass, which would mean that the MHU squared, it would also be in the order of mz squared. Now this would imply, if you look at the RGE running, that you would get a negative contribution from a large gluino mass And the top you cover contribution, which is positive, the neutrino mass would be negative and running up. The top you cover coupling would be large. Sorry, would be smaller than neutrino mass. And this might imply that at an immediate scale you would have that the stop mass parameter for the right stops could turn negative, implying potentially the need for new physics at an intermediate scale before the gut scale comes, which would be quite interesting. But as it is only as a side remark. Now, as I said before, what this type of scenario lacks is our dark matter candidate. Which brings me to the second part of this talk, namely extended models. What I have in particular in mind are actually models that have extra gauge groups. They are motivated because we have a different d terms contributing to the Higgs mass at tree level. For example, if you have an extra U1 high, as you would get from SO10, this would be the additional U1 within SO10, which is orthogonal to the standard model group. You do get a contribution which corresponds to the electroweak coupled G's high here, that's approximately as the size of the hypercharge coupling, which boosts up the tree level to the order of 100 GeV instead of the Z mass. In the term of the breaking of SO10, you could also explain why R bar is conserved, because this will depend on the breaking of the U1p minus L, where you have either conserved R parity or spontaneously broken R parity. You can explain in this class of models easily neutrino masses because the SO10 representations do contain the right-hand neutrinos. And there you can have either the usual seesaw mechanisms or the inverse seesaw. Most interestingly, if the mass scale of the right neutrinos is at the electroweak scale, you have the possibility to get the right neutrino, the supersymmetric part of the right-hand neutrinos, or another exotic scale as a dark matter candidate. And this might be interesting in combination with natural supersymmetry, which will occur in a modified form now. For those who are not very familiar with neutrino physics, let me briefly summarize on this slide here the idea of the inverse seesaw mechanism. So it would be in a base, it would have here the left-handed neutrino, the right-handed neutrino, and some additional neutral fermion carrying lepton number. This would be the ordinary Yukawa couplings. And this would be Yukawa couplings coming from a different Higgs boson between the right-hand neutrinos and this additional fermion. This mu s here, this would be a lepton number where a leading mass term, which is assumed to be small. Now, this of course would be 3/3 generations in the most generic case. Let's go now to the limit. We have only one generation. This mu s is 0. Then of course this one here are all scalars. This would be 0 entry, and you could immediately solve this system. You would find you would have a 0 mass eigenvalue and a Dirac pair. In this way, even if the Yukawa couplings here are large, they can be as large as top Yukawa coupling, you would get here in this class of models light neutrinos together with a relatively heavy, more or less Dirac-like pair. So you would have a light neutrino case if you assume mu s to be non-zero, plus a quasi-Dirac pair which is relatively heavy, which means a few hundred GeV in our case. Of course, as this neutrino sector would be much more complicated. I just showed this the complexity. I don't go into details here. As the other leptons or fermions in general get some additional d-term contributions, I just give here the example of the leptons. So you have the usual left lepton part here, right lepton part here, left-right mixing part in the off-diagonals here. And usually D parts, you have the MZ contribution, but now you get from the additional Z prime, the extra U1's contributions of this form here. And this has quite some impact on the masses. So what I show here as an example is fixing some high-scale parameters, which are still consistent with current experimental considerations, apart maybe the Z prime. And then you see the spectrum fixing the soft Susy breaking parameters at the high scale as a function of the Z prime mass. And the light neutrino here is actually more or less a singlet neutrino. So it's a potential candidate for dark matter here beside the neutralino here, which in this context would be more or less Ticino-like. So here you would have the usual hierarchy, left leptons, right leptons, they're somewhat heavier than the stars, neutralino. Then you would have the light neutrino. Or you would have here in addition the light neutrino. Or if you go to this part here with rather heavier Z primes, would actually have a rather compressed spectrum between the left leptons and the right leptons heavier, so opposite what you usually would expect in a CMSM-like context. And you would have the neutralino in between the right leptons and the left leptons, and the LSB would be again the neutrino. But this would be a good dark matter candidate or not depends really on the details of the parameters in the neutrino sector of the previous mass matrix. It has to be really investigated in detail. So that's not the claim that over the whole line, every point corresponds to a good dark matter prediction, or let's say explanation. But some part of this does it. I think, if I remember correctly, this part here around 2.8 to 2.9 TeV. Now the current limit on the Z primers in this model is actually close to 2.2 TeV. It's somewhat smaller than the usual limits, because in this class of models you have an effect called gauge kinetic mixing, which alters the cross sections for the Z prime as well as the branching ratios. As this quark sector shows some dependence, you get a somewhat larger hierarchy, but that's not too much different from what you usually have in SUSY models. Now, in this class of models, you have relatively light right-handed neutrinos. So they might appear in the cascade decays of the SUSY particles. We should have a look what they induce via the decays. So they can decay either into W in the lepton, or Z in neutrino, or into Higgs boson, the lightest one usually, plus a neutrino. Roughly speaking, what one finds is, if you look at the branching ratios of the into W and charged leptons versus Z neutrino or Higgs neutrinos, it's roughly speaking 1/2 to 1/4 to 1/4. The reason being that's mainly given by the boson component of the gauge bosons and therefore of the Higgs boson. You can play parameter space in this class of models and find there are a couple of points where you get SUSY decays, but they're never large, at most a few percent. So really, we essentially have standard model decays for this class of scenarios. We have a lot of changes in the SUSY cascades. I'm just depicting here the most prominent ones, because usually what you have is in CMSSM gauge mediation that the right quarks decay straight into a jet, plus the lightest neutralino giving rise to a very hard jet plus missing energy. And several of the bounds for SUSY searches comes actually from very hard jets plus missing energy searches. Now, what you see here, these points are different standing points created for this type of models. And essentially what you find is that there's scenarios where the decays into quark and neutralino as usual, but now the neutralino is not stable, but decays further into neutrino, this neutrino. This shouldn't. And then the neutrino decays further into one of the lightest neutrino plus a Z boson or W. Or you can even have this heaviest neutrino which decays further into the lightest neutrino. So you have a lot of additional electroweak stuff and leptons compared to the usual signals of one jet. Or you can really have here where you can have a decay into one of the heavier neutralinos, which would be in this case the gauchino of the extra U1, and this would decay further as again into leptons, Ws, and so on. Similarly, the scenarios where really the neutrino is lighter than the neutralino have a lot of additional leptons, in particular if these leptons are lighter than the neutralino, as we have seen in the plot before. So what you find is that you have enhanced multiplicity, particularly for leptons and jets. The jets where the leptons are much more important now compared to the CMSSM. So what we did was actually to take natural SUSY scenario. So take all the stuff that I've shown before. I stop light, let's say light Higgs-Zenos, assume that actually the stops and neutrinos are just above what can be seen, but take this lepton slide, motivated by the fact that the d-terms can reduce the masses for these leptons. Now what we had was just the right hand, the superpotential, the MSSM part, plus some mass term, which corresponds to the Werner mass term for the right hand neutrinos, plus the cover term. And then you can express your canvas in terms of the so-called R matrix and the causal parameterization, where, for example, like it's shown here in this particular case, cosine and sine of complex angles appear. And they imply that in the canvas you can have cosine hyperbolicus of a parameter which we denote here by gamma 5,6 times a phase factor. And the cosine hyperbolicus implies that you can easily get an order of magnitude or 2 orders of magnitude in the size of your cover couplings compared to the usual case. And that's what we assumed here, taking the lightest neutrino to be order KV, so they can potentially serve as a dark matter candidate in addition to this neutrino. And the M5, M6, this can be ordered few to order 100 GeV. Later on, we assume that's actually 20 GeV for fixed number. Now, as I said before, we assume that these leptons could be light. So what one sees here in the plot, I hope it's visible, are the cross sections of the different channels. So the largest one would be the Young process where you have the left lepton with the right with the left neutrino together. Then we have the left leptons be charged or neutral pairwise, and the right leptons would be the least important ones. So one immediately sees by looking at the order of magnitudes, the most important constraint will come from the Young process producing one neutrino together with one left lepton. Now their dominant decays are actually either into a lepton at the lightest neutrino or into neutrino and chargino. And depending whether the neutrino 1 is the LSB or not, we would stop here. If this neutrino, the R neutrino is lighter than the neutralinos, this would decay further into a neutrino and this neutrino, so you would have missing energy here. And here you would get, for example, from neutrino decay into a lepton and the R neutrino, so as a lepton plus missing energy. And similarly for the left neutrinos. So what we looked at was a different scenario. One will really have the Higgsino LSB. So we stop the cascades at the neutralino level. And what you see here in this plot are the left lepton mass parameters, the right lepton mass parameter. We fixed mu to be 120 GeV and then beta equal 10. And we use the ATUV data plus the 13.9 inverse femtobond data at 13 dV within the so-called checkmate package. So what you do, you give in your model points to a Monte Carlo sample, you plug in the Monte Carlo sample, the checkmate, atomization is done, and then it's compared to the available Atlas and CMS studies inside this package. The most important ones for our considerations were the 2 lepton plus missing energy searches. Now, the package itself gives you one parameter called R, and it tells you if R is smaller than 1, then the point is excluded. If it's larger than 1, it's allowed. But of course, you should take into account statistical uncertainties, cross-section uncertainties. So that's what we did. So we said, okay, let's take a 10% margin on this R value. So if it's below 0.9, then a point is excluded. That's the red point here. If it's above 1.1, then that's allowed. And everything in between should be studied more carefully. And that's what we would call ambiguous. So we see here the left lepton masses, if they, let's say, are 4 GeV or below, that's excluded by data. If they are heavier, then the R leptons, which have a significantly smaller production cross-section, come into game. But there the bound is only, roughly speaking, order 200 GeV. Now, of course, these are 13.9 inverse femtobonds. The additional data now order 35, 36 inverse femtobond. There, here, these points would start getting red, becoming, so as we look at the exclusion, my guess would be, can get the exclusion up to 20 GeV, taking account the full set of data available. Of course, the mu parameter is relatively small here, so the question is what would change if you increase mu. That's shown here on the right plot. So the blue line here, that's the diagonal part here, taking ML tilde equal ME tilde, and going along this line here. So that's the uncertainty band here. Then we took the green line mu equal 150, the red line 200, and the black line 250. And you see, of course, the bounds grow up. the part here decreases because we have less phase space, which means we have very soft leptons, and therefore they're not sensitive. Then there comes the part where we're sensitive, and then here, roughly speaking, we can get to the same part as long as the sufficient phase space. Now, if mu gets about 250, we don't have yet sufficient phase space anymore for hard jets and significantly large cross section. So you wouldn't get any bound there anymore. So the left lepton could go down to, let's say, order 270 GeV. They would not be sensitive within the current LHC data. Of course, more interestingly is actually that the R neutrinos at the LSB. And there we get an additional constraint from the direct pair production of two Neutrinos, which would then decay further into leptons. So that's shown here. So what you see here is this neutrino mass versus the mu parameter essentially is the mass of the Neutrino. And you see with the data set available, we can exclude, roughly speaking, masses up to orders 270, 370, 380 GeV. If this neutrino is light, of course, if it's again order 200 GeV, we don't have any bounds because the leptons are not sufficiently energetic to pass the cuts for the analysis. So essentially, you see we have here a band where we have relatively soft leptons. Therefore, we're not sensitive again. So the color coding is again red excluded, green ambiguous, blue allowed. So we actually choose lepton masses in this band here. That's the plot that you see on the side here. The mu is chosen to be 25 GeV plus this neutrino mass. And this should be, of course, smaller than the lepton masses, where we set equal the left lepton mass parameter with the right lepton mass parameter and the joint axis here. So what you see here, if there's sufficient phase space, we can get up to order 550, 600 GeV for the lepton mass parameters. If we now turn to the part here, so the bounds are given here, sorry. This part here is essentially cross-section. We don't have sufficient statistic. This part again here is the hardness of the leptons, which gives us the boundary. Now going to this part here, we can fix, for example, the mu parameter 4 GeV, which implies that here these leptons only have 3 body decays, or decays, for example, of a left lepton into charged left lepton into a W and an R neutrino. But of course, this would imply this mode is relatively small, has small branching ratio because you have a relatively small left-right mixing in this neutrino sector. So essentially, what you have here are 3 body decays mediated via virtual Higgs. And then what you find is actually you have a lot of Higgs bosons, W's, and Z's into the final state plus missing energy. And it turned out that at least in the analysis implemented in checkmate package, which were quite a lot, they're not sensitive in this region here. So there are parts where we can go down with lepton masses to 200 GeV and you would not be sensitive in this class of models. Above here, you have 2 body decays, and you have similar constraints as before. Below here, actually, parts of the parameter space we have sufficiently energetic leptons in the cascade decays, so boosted W's, so again sensitive to the analysis. This brings me to my conclusion. So what you have seen here is that the bound on the Higgs mass and combination with no base emphasis is actually consistent, because we would have to have relatively heavy spectrum, the SUSY spectrum. At the same time, we would have in unified models relatively large A0 parameters. There's the danger of current charge breaking minima, which should be looked at. In general MSSM, we could have the possibility of compressed spectra, and there are few GeV for the SUSY would still be allowed. Particular class, as I've discussed, are natural SUSY. You have only the state slide, which contribute at the loop level to the Higgs masses, but they have this disadvantage in the minimal versions they cannot explain dark matter, which motivated me to go to extended gauge groups. Then there's a neutrino physics automatically included. You can easier get a mass of 125 for Higgs without that large corrections, so the charge and color breaking minima are less important. And then we could have this new R, the part of the right neutrino, as a LSB this would be compatible with dark matter the density considerations, but you would avoid, because it's a gauge singlet, essentially the dark matter constraints from direct searches. And then we have seen as one example, if you have natural SUSY plus the right neutrino, the bounds on the SUSY particles as given here. Thank you very much.
Okay, thank you very much, Werner, for this very interesting talk. Let's see. Okay. So I'm wondering if there are any questions from the audience.
Yes.
Who is this? Oh, there you are. Diego, please go ahead.
Hi, Werner. How are you?
Fine, how are you, Diego?
One question about the last model with right-handed neutrinos. What happened with stars? Because in principle, you can have the stars lighter than the first generation of leptons. There is an exclusion there.
Actually, from the star channels, the exclusion are much less important than for the first two generations. The reason being that the taus are much harder to detect at the LHC due to the hadronic decay modes. So I had today actually a talk with somebody from CMS, and they are currently finalizing their analysis. And he told me, well, that's half of the range that you get for the first two generation of leptons for the direct searches. So for this type of consideration that we had here, the taus are much less important than electrons and muons. So even if you take the taus somewhat lighter than the left leptons of the first two generations, the picture will not change much here.
Okay. I don't know if there are any other questions from the audience. Well, I do have one question, which is about the D terms given by these U1 extra symmetries.
Yep.
So you said that you could enhance the Higgs mass by about 100 GeV, the tree-level Higgs mass.
Yes.
Right. So what gives you that upper bound to the tree-level contribution?
If you look, when you're in the MSSM, look at the mass matrix, it's essentially, it's only the D terms at tree level. And usually you express them plus the mass of the pseudoscalar Higgs boson.
Mm-hmm. Right.
So in these extended gauge models, we do have more or less the same structure, but in addition to the usual D terms of the SU2 and the U1 hypercharge, you have this U1, this case which we call chi. Then, of course, you can express the usual SU2 and hypercharged contributions as the Z mass. This gives the mz squared, plus the contribution comes from this additional vector boson. Or let's say from this additional gauge group.
Right.
So for the calculation, I can give you the paper later on. I don't really have it now written down here.
No, well, but from that plot, I was wondering, because you can always make the VEV higher.
No. The VEV that appears here is the SU2 VEV.
Ah.
It's not
of
the additional vector boson.
Oh, I see.
But I don't understand that.
The reason is what you have is a mixing of the Z with the Z prime. And this gives you this additional contribution here.
I see. That was Oscar, by the way.
Okay, I don't know if it works.
Well, essentially what you have is you have an off-diagonal term which goes like VEV times the SU2W VEV times the VEV of the extended sector, let's call it VR. And then if I make approximate seesaw diagonalization, you get this part squared divided by the mass of the extra gauge boson. which gives in this case the VR squared. Then you're left with the vector weak web squared here.
Okay.
I have a question.
Yep.
So in these models, have you looked into models with an additional singlet that can give you an additional 3-level contribution to the Higgs mass, and also give you additional neutralinos?
No, we did not include an additional gauge singlet in this class of models. But this model has a curious feature that indeed from the expanded Higgs factor, we do get an additional Higgs boson, which comes from the Higgs fields giving weft to the Z prime, which is relatively light, which means order 100 GeV.
Oh, okay.
But it's not the singlet that you have of the usual NMSM.
Mm.
This would be more these things you might know, these papers by Geneviève Bélanger and collaborators, where they had this anomalous U1, where you have this NMSM Higgs boson, which was charged under this anomalous U1. It would be a similar situation.
And on these models, you have an additional gauge boson, right? And it has to have a mass. Have you looked into so how small can this mass be?
Well, taking the bounds until last spring, so this means roughly speaking more yaw. In this class of models, it can go down to, let's say, 2.2 TeV. So that's roughly speaking the bound.
2.2 TeV or GeV?
TeV.
GeV, okay.
No, TeV. Teraelectron.
Okay. Because I mean, I guess you can also have supersymmetric kinetic mixing of this new gauge boson with.
There is gauge kinetic mixing between these Z primes with the usual one form.
Okay.
That's actually important for the terminology because this will alter the couplings of the Z prime to quarks and leptons.
Yes.
Then you see if you really make the assumption that at the gut scale you don't have any gauge kinetic mixing, when you use a sizable mixing at electroweak scale, it actually reduces the cross section by up to 40–50%.
What about the other end of the spectrum? I mean, can you make this dark photon really, really light?
That's not a dark photon.
Sorry, this dark, this U1 gauge boson.
No, you cannot make it. It couples to standard model thermions.
Okay.
So the usual searches apply, but they get modified because of this gauge kinetic mixing.
Okay. Thank you.
You're welcome.
Well, maybe I am Oscar. Maybe I can ask something also. Hi, Werner. Well, about this X U1X, I see that this U1X is apparently a combination from UR and UB minus L, no? Isn't it?
Orthogonal one to the hypercharge.
Orthogonal to the hypercharge. And so I assume that the Higgs particles, the Higgs doublet, is not charged under this U1X.
That's true.
Because if not, the B that we have above would be the B of breaking of U1X. I would assume.
Yes.
So then why you have 1/4 G kappa? That I don't understand. You said it's because of the mixing, but I would expect some kind of a small mixing between the gauge bosons.
Yes, the mixing is really the WF divided by the VR. That's also the mixing the Higgs sector. Higgs sector, but it's really remnant if you make this type of approximate seesaw formula in this Higgs sector that you get out this term here.
I see. So it's similar to the seesaw formula for this.
Yes.
With the two BEPs, I guess.
With the two BEPs, yes.
Okay. And another question, how does it affect to the other Higgs bosons? This U1x.
I must admit we never looked into that, so I cannot answer this.
Well, probably it will not affect much, but I don't know. It could be interesting. By the way, have you heard that there is a possible excess at 440?
I had heard some rumors, but I did not take them too seriously, I have to admit.
Well, I don't know. I saw it is published in the note, but they don't make a big fuss of it. It's in a paper.
Okay, I didn't know that it's in a paper.
Yeah. I had the reference somewhere.
So maybe I will send you later an email.
Yeah, that last note. Could be interesting for these things. Okay, that's it.
Any other questions?
Yes, hi. A brief question first. You in the constraint, the M-SUGRA model where you have color and charge breaking minima. I assume that if you go to the NMSSM, those constraints totally relax, right?
Actually, not. There was.
Why not?
Let me remember. I think it was a Korean group who looked into that. And there are parts of your parameter space that it does get relaxed, but they also found parts that's really still a strong constraint.
Okay, thanks. I mean, okay, if you find, then the reference would be nice if you send it.
I can do that. You're Federico, aren't you?
Yes. Hi. Okay, and I have another brief question. I hope I state correctly. In one of the, when you have your right-handed neutrino, you enhance the Yukawa couplings, basically doing a mixing with a hyperbolic angle, right? Now, this is giving you with some seesaw mechanism the masses of the neutralinos at tree level. At some point, you'll need to do radiative corrections to those mass terms, right? So how far can you go before that breaks down?
We don't know yet. That's actually a project we are currently we plan to work on. So can I give you the answer?
Right, thanks. So how far do you go actually in your analysis? I didn't see that.
So what we took here was 20 GeV for the right-hand neutrinos. And well, can you remind me? I forgot to write down the number what we took for the gamma 5, 6, I think it was 8. Can this be?
Yes, it was about 8, so that it wouldn't have any issues with the lepton flare violation.
Yeah. So the Yukawa couplings here are still order 10 to the minus 4.
All right, so it's pretty small still.
Yeah.
Thanks.
I don't think that radiative corrections are really an important issue in this part of the parameter space we looked at here.
Okay, any other questions, maybe? Okay, let me finish with one question. Still with the D-term contributions, I was wondering what happened with the loop contributions to the Higgs mass, because then the stops are also getting D-terms, right? Extra D-terms and things like this. So wondering, how did the loop corrections change?
Let's go this way here. What you see here is essentially the D-terms MZ depends on this MZ prime here via the D-terms. So we have essentially the same D-terms as above here, but the prefactor changes. I think this for the right stop, that's 1/4, but I would have to look it up. So you see, it depends relatively mild in case of these quarks because they already have relatively heavy masses.
I see.
I should say here that the Dunn beta R was fixed with 0.94. Turns out you cannot go too far if you want to have mz prime up, let's say, to 560 V, if you want to avoid tachyonic states.
Okay.
So the cosine 2 beta r is not that large. It doesn't get to order 1. It's more in the order of, let's say, 0.1 or below.
Okay. So any last questions? Let me check the YouTube channel if there are any other. No, so nobody from the live chat. So okay. All right. So there are no other questions. Oscar has sent the link to the paper that he talked about. So maybe we can discuss that offline or something like that with a bit more time. So okay, if that's it, I'd like to thank you, Werner, for giving this very good talk.
Thanks.
And yep.
Sorry it took so long. I just realized that's more than 40 minutes.
Oh no, it's perfect. It's perfect because the whole thing just lasted 1 hour. So great. So anyway, before we log out from all of the people here, we'd like to send our virtual support to our friends and colleagues and everybody in Mexico who are having a very hard time right now. So please hang in there. We'll see those very soon. Okay. Thank you all. See you around.
You.